Modern enterprise systems handle hundreds of millions of data points every second. At that scale, a database functions as a rigid, exact mathematical structure. Based on relational theory, this structure is built on two primary components: relations, which we commonly call tables, and tuples, which we recognize as rows. This table is our test environment, a standard employee relation with four basic attributes. As data populates, we see two distinct employees sharing the exact same name, Aman. Querying this name creates a fatal ambiguity. The search splits, unable to return a single deterministic result. In relational theory, a database is mathematically invalid if it cannot deterministically isolate every single tuple in a relation. Ambiguity equals structural failure. To prevent this collapse, database engines rely on a specific mathematical mechanism for identification, the superkey. The superkey is the foundational concept behind all database key theory. This text defines the rule strictly. A subset K of a relation R is a superkey if no two distinct tuples have the same values on all attributes in K. In practical terms, a superkey is any combination of columns making every single row unique. Applying this rule to the employee ID attribute, we scan the data. No two values are identical, guaranteeing uniqueness. It is a valid superkey. The same logic applies to the email attribute. Every distinct address makes the email column another independent, valid superkey. These single attribute superkeys mirror the way we identify people in the physical world, using distinct identifiers like a passport or a social security number. As long as an attribute passes the strict test of tuple uniqueness, it forms the mathematical bedrock required to make data retrieval precise and reliable. Single columns are straightforward, but evaluating sets of multiple attributes often traps beginners who focus only on the smallest possible unique set. Consider this. Employee ID alone is unique. What happens if we combine the ID and name? Executing the uniqueness test reveals a mathematical certainty. Because the ID never repeats, the pair is distinct. According to formal definition, this isolates every tuple. It's a valid superkey. You might immediately recognize that the name attribute is technically redundant here. It is not required to identify the row. However, the definition of a superkey requires uniqueness, not minimality. Redundancy does not invalidate the key's ability to unlock the correct row. This leads to the superset property. The superset property states that if a set of attributes is a superkey, adding any other attributes to that set creates a new valid superkey. We can push this to the extreme. If we combine the ID, the name, and the department, the presence of the ID still forces the entire combination to be unique. Even with multiple redundant attributes, this set meets the mathematical criteria. A superkey is defined purely by its capability to isolate a row. Carrying extra attributes makes the key inefficient for storage, but mathematically, it remains a valid superkey. In a production database, an engine cannot pause to manually check millions of rows for uniqueness. It needs an algorithmic way to prove a superkey exists. To accomplish this, database systems map out relationships using functional dependencies. This diagram introduces the notation x arrow y, which means x functionally determines y. This means that if you know the value of the determinant, in this case the employee ID, you are guaranteed to know the exact values of the rest of the tuple. This yields our algorithmic rule. If a set functionally determines all other attributes in the relation, then that set is a superkey. We can also express the superset property using this algebra by adding the name attribute to the left side of the dependency. Because the ID is still present on the left, the equation holds. Adding an attribute to the determinant side never breaks the functional dependency. Functional dependencies elevate the superkey from a concept into a rule. Engineers use these rules to calculate and verify every valid identifier in a schema without scanning a single row of data. While having dozens of redundant superkeys is mathematically true, building a clean database schema requires filtering them down to what is practical for implementation. To do this, relational databases use a nested hierarchy. The outermost layer contains the universe of all superkeys. This includes the efficient single attributes alongside every possible redundant combination. We apply our first filter to extract the candidate keys. A candidate key is a minimal superkey. The test for minimality is simple. If you remove even one attribute from the set, does it lose the property of uniqueness? The combination of ID and name fails this test because removing the name leaves the ID, which is still unique. But the single ID and the single email attributes are minimal. They pass. Finally, we reach the innermost layer, the primary key. The primary key is the single candidate key chosen by the database designer to enforce referential integrity across the system. This establishes a strict hierarchy. Every primary key is a candidate key, and every candidate key is a superkey. The reverse is not always true. Applying this hierarchy separates a bloated table structure from a streamlined, efficient architecture. This theory directly dictates how advanced data systems ensure data integrity. This graphic shows the constraint for Boyce-Codd normal form, or BCNF. It states that for every non-trivial functional dependency from X to Y, X must be a superkey. BCNF eliminates data redundancy by ensuring that every determinant in the relation acts as a valid superkey. Establishing a correct normal form is impossible without first identifying the superkeys within the schema. These foundational definitions provide the precise mathematical logic necessary for maintaining absolute consistency across massive, globally distributed database systems. Understanding the superkey is the technical prerequisite for designing the architectures that manage the global flow of information.